Morning, everybody. Nice of you to join me. It's a packed room, so that's nice. Today we're going to have some fun with coroutines, as you can see here on this beautiful Photoshop picture. So who am I? My name is Riccardo Lippolis. I'm a software developer / architect working at JDriven, living in the Rotterdam area, currently working at Makkie, doing a project. Makkie is one of the sponsors here. That's not why I'm here, by the way. They really like my abstract, apparently. I've been doing Java development for more than 10 years now. In the last few years, been focusing more and more on Kotlin because, yeah, it's awesome. And also doing some talks about, well, initially about reactive programming, the principles lying behind that, and then ultimately shifted to Kotlin, the language, and then also Kotlin Coroutines, which also has some links with reactive programming. For example, last Kotlin Dev Day, I did a presentation about concurrency made easy with Kotlin Coroutines. And the reason why I'm giving this talk is because every time I was giving the concurrency made easy with Kotlin Coroutines talk, at the end, I had a few slides with some fun with coroutine stuff. But because I was always talking so much about coroutines, I always lacked a bit of time at the end to really properly dive into these things. So I thought, well, I'll create a new presentation where I can really focus on that part, the fun part, at least for me. So what are we going to talk about? Well, we're going to discuss channels, flows, supervision with coroutines, ThreadLocals. I wanted to talk about actors as well, but while I was preparing the presentation, I already saw that the developers of the coroutines library said, well, the way actors are implemented now, it's not how we want it, so they're going to change it. So I was like, yeah, I can demo it, but it's going to change anyway, so I dropped the actors part and instead focused a bit on debugging, which was really needed while developing my demo. It came in handy. So how am I going to explain these concepts? Well, I want to have some demo application that I could use to demo all these different features. So I thought, well, coroutines, that's like asynchronous stuff, data streams from A to B. So what to build? Well, you can think of something like messaging system. And when you think of messaging nowadays, most people think, oh, Kafka. Well, maybe nowadays it's becoming more towards Pulsar or something, or maybe some of the older people in the room still favor JMS, which is also fine. But Kafka is still very popular. So I tried to build my own Kafka with Kotlin Coroutines, and I called it Kotka. Of course, because, well, people are aware, like, yeah, Kotlin, that's an island, Java, it's an island. Well, I thought I have to do something with geography, so Kotka is actually a place in Finland, for those that don't know. So that came in handy. By the way, when I came up with this name, I Googled it to see if anybody else was using it, and unfortunately, I was not the first one coming up with Kotka, but the other ones were using it in different contexts, and this was just a demo. It's not production stuff, so no copyright issues probably. But yeah, it's just for fun. Don't use it in production. So what's the architecture of Kotka? Very simple. We have a server built in Spring Boot. I use Spring Boot for all the services just because I am handy with Spring Boot. It's not that I say you have to use Spring Boot. There are other very valid alternatives, but I use Spring Boot because I like it. So the server has two endpoints, a produce endpoint and a consume endpoint, both WebSocket endpoints, because then you have like a flow of data going back and forth over WebSockets. And there are one or more producers, well, basically 0 or more, but it's more fun to have at least one. Which communicate with the produce endpoint. They send their messages to the produce endpoint on topics, which are just strings. And there are consumers which can connect with the consume endpoint, and they read the messages. Well, they subscribe on topics that are produced by the producers. So just a quick demo to see that it actually works. I'm already running them. So at the bottom, you see the server application. I hope it's readable. So what you see is that I have a number of producers. In the top left, you see the produce application, which produces on different topics. I didn't know what to come up with, so I just used a random data generator library to come up with these messages. So in the at the producer side, you can see that we are producing, well, Chuck Norris quotes, Big Bang Theory quotes, Brooklyn Nine-Nine quotes, and some beer names, which are also random. And in the top right, you see that the consumer is receiving those messages. Oh, it scrolls back. Well, anyway. And what you can see here also is that both the producer and consumer basically only work on the main thread, which is not entirely true, but at least the message processing happens on one thread. And it's maybe not the wisest idea, but I thought it was just cool to try if I could make that work, and it did. And in the server, you see that there are multiple worker threads handling the different connections, which are basically provided by the netty layer, which is basically the I/O pool of the Spring Boot application. And you can also see in blue that I added some extra information to the logging using the MDC logging context to show which producer is producing this log message or which consumer, to give more insights in the specific log message, and also to see that even though you're running everything on one thread, in case of the producer and consumer, we're still handling multiple things at the same time, which is ultimately what we're using Coroutine for, right? So, okay, how did I build this? Well, first off, one of the main concepts that I use a lot is the concept of a channel. A channel is well, basically a class provided to you by the Kotlin Coroutines library, which allows you to transfer data from a sender to a receiver, or actually from multiple senders to multiple receivers. It's just a very, well, I mean, it's pretty nifty how they make it work, but it's very simple in terms of usage. You can produce messages on one side, and on the other side you can consume those messages, and it's all non-blocking in the sense that it can suspend, but it won't block. So you can compare it to a blocking queue, which is present in the Java library, but yeah, without the blocking part. It's more like a suspending queue. So how does it work? Well, to create one, we just call the constructor, and we get a channel. In this case, we say we want a channel which produces and consumes strings. Of course, you can use whatever. In this case, it's string. The channel class itself implements two different interfaces, a send channel and a receive channel. And basically, that allows you to, for example, when you define a function, say, OK, this function needs a send channel. So we only need to send messages. And then in another function, you can say, well, in that part, we only need to receive messages. So it makes it clear. But in essence, it's the same underlying class. Well, to use them, to consume messages from the channel, a very simple way is just to use it in a for loop. So in this case, we just iterate over the receive channel. Of course, that can also be channel, but not send channel. And we print whatever is received from that channel. There's also a receive function, which is suspending, which allows you to get the next item. So you can do more advanced constructs, but this is just the very simple way of reading messages from a channel, like very elegant. So in this case, I launch it in a separate coroutine, because after that, I use the send channel to send messages to the channel, and there's just a send method, and it prints hello world. So very easy, simple construct. So it has a few characteristics. The channels are fair. Makes sense that it's first in, first out, like a blocking queue, and it's not only first in, first out for the messages, but also for the ones producing and the ones consuming from the channel, which means that if multiple producers are sending messages to the channel, they are also handled in the order of which they are called. And if multiple consumers are reading from that channel or receiving, they also get the messages based on whoever calls receive for the first time, like the fastest, basically. So it's not necessarily a round robin, but if you call the receive method round robin, then you get round robin message processing. But it's not that every consumer gets every message, so you get the next message from the queue. They are closable, so that means that, well, they have a close method, and if you call that, it closes the channel for sending new items. But if there are still items in the channel, the receiving side can still process those items. And when the last item is received, then basically the channel is closed and done. And that means, in case of the for loop, we saw earlier that the for loop is done, is terminated. So it's very simple. The moment you exit from the for loop, basically that means the channel is closed. And you can also cancel a channel or close a channel by canceling the coroutine the channel is running in. So it's also like it matches the principle of the structured concurrency that we know from coroutines. Channels can also buffer elements. So basically the standard implementation is what they call a rendezvous channel, which means that if you send something to the channel, there has to be a receiver receiving that message. If not, the send function suspends. So that means the producer is, well, suspending until there's a receiver or a consumer reading that message. And the other way around, if you call receive, or if you're in the for loop, it will suspend until somebody sends something to the channel. But maybe sometimes you want to, well, add some buffering. So what you can do is you can create a buffer saying either a fixed size, or you can also just do an unlimited buffer, which is of course not recommended due to memory constraints. But you get nice, sort of like a back pressure thing. You can buffer a few elements, but if the consumers can catch up, then that's fine. So how did I use them in my application? Well, basically a WebSocket connection can be seen as both a send channel and a receive channel combined, sorry. Because a WebSocket is basically a full duplex connection where you can send and receive data simultaneously. Well, we can abstract that away in a data class, in this case, which has a message consumer, which is a receive channel of some type of data we get from the other side, be it the server or the client, depending on which you are. And the message producer, which is a send channel, which you can use to send messages to the other side. And that makes the processing of messages, the whole communication between the client and the server very easy, very elegant, in the sense that the processing of the messages on the receiving side is basically a for loop. And every time you get a message, you can do whatever you want. And to send a message, you just call the producer .send, and it's sent. And that's very nice abstraction over the WebSockets. Of course, behind the scenes, I needed some work to actually make it work with Spring Web Flux, because, well, Spring Web Flux has nice integration with Kotlin Coroutines, but only if you're using traditional controllers, like REST controllers, or not when you're using WebSockets. You have to do some custom work. But yeah, I hid that all away in one ugly class, which I still need to refactor, but you know that's never gonna happen. So we found a way of connecting senders and receivers with each other, but of course, we also need something to send, right? So for that, we can use flows. A flow can be seen as an asynchronous stream of values. So it's kind of like a sequence in the sense that you get an arbitrary number of items every time you say, hey, give me the next one, but with one added component, and that's the time component. So when you call, we ask the flow for the next item, it might take a while. So there can be a delay. So those familiar with reactive programming might think, oh, it's like an observable. Yeah, basically has some overlap. Yeah, so how do you create a flow? It's kind of like creating a sequence. I don't know if people have ever used the sequence builder, but basically that means declaring a block, a code block with a sequence builder saying, okay, I have a piece of code that yields items on the sequence. And for the flow, it's basically the same, but you can also call delays, have more suspending capabilities than in a sequence. So in this case, I just have an incrementing integer which starts at 0 and emits every second emits the next item. Well, it actually starts at 1 because I have ++i. So every second it emits an item, and I can just use a while true like an infinite loop here because, well, the delay and emit are suspending functions. So whenever the coroutine is cancelled or cleaned up, or your stop reading from the flow, it just stops. So there's no like hanging thread or whatever. You can also create flows based on a static set of data. So you have like the flow builders for basically it's the same as sequence of or list of. But yeah, if you already have a static set and you want to convert that into a flow to do some further processing, it's very easy to do. And to consume a flow, you have the collect method. So the collect is it's a suspending function, but it's also a terminal function in the sense that it will try to collect all the items from the flow every time a new item is emitted on that flow. So in this case, I use the take 5 to limit it to only 5 items. So in this case, it will print for 5 seconds, 1, 2, 3, 4, 5, and then it stops. Also very easy. So another way of terminating the flow collection basically is by just canceling the coroutine, as I said before. So in this case, we launch the collection of the ticker flow in a separate coroutine where we say, well, we map the items and we multiply them by 2 and then print them, but we don't limit it in any way. And then outside of that coroutine, we just wait for 2.5 seconds and then we cancel the coroutine, and that means it will stop collecting as well. So and it cleans up itself. So that's very nice. So in Kotka, I use it to generate basically the fake data that is sent by the producer. So in this case, I use Faker, which is from the data Faker library, which is a nice library which can generate a lot of random data for you. In this case, it generates Chuck Norris quotes. And in this case, I just use an infinite loop to generate facts on that flow. You can see that I don't add any timing-related stuff here. So basically, it's like a sequence, but I'm adding the timing to it later. And that is because I wanted to have sort of like a configurable delay between the messages. So instead of handling that inside the fact generator, basically I took it out and used the onEach, which, well, on each item executes some suspending function. In this case, it says, well, add a delay of 1 second. And in case of my actual code, I have a random delay between the minimum and maximum value. And then in the collect, I just call the message producer.send, and it gets sent to the client. Well, in this case, it gets sent to the server, and the server can send it to the consumers. What's also nice with flows is that it doesn't have to be like a totally generated stream of values. You can also define behavior with it. So in case of a WebSocket client or Kotka client, consumer, you might say, well, okay, I want to start by subscribing on the Chuck Norris and the beer topic. Then I want to wait 10 seconds, and then I unsubscribe from one topic. Then I wait another 10 seconds, and I unsubscribe from the beer topic. And then you have the whole behavior of your client basically defined in one flow, which is easy to test some different scenarios of how a consumer would interact with the server. So far, basically, the way I was creating the flows was in a way that's called a cold flow. So for those familiar with reactive programming, you have the cold and hot observables. The way you can explain these concepts is basically a cold flow is like a Spotify playlist. You know, the moment you start listening to the playlist, it starts from the top and just goes through the playlist until it's done. If you start it again, you get the same songs again. A hot flow is more like listening to the radio. So the moment you start subscribing or collecting from the flow, that determines what data you get from that flow. So when you start listening to the radio, you get some song, and another moment you hear something else, which is obvious. So that basically is the difference between a cold and a hot flow. So hot flows are also possible, and there are two ways of doing that. One of them is called, well, it's basically a buffered flow, which is called mutable shared flow. It's, you might think, hey, but we're doing Kotlin, we don't want mutability. But yeah, okay, so it's not like globally mutable. Basically, the idea is that you locally produce items on that flow, and it gets broadcasted to multiple consumers whenever they start consuming. So it's like a I don't know if people have been experimenting with Kotlin Coroutines a while ago, but there was a thing called broadcast channel, which was a channel where you could send something and then it got broadcasted to all the consumers. Well, basically, this is the replacement of that one. Another one is called mutable state flow. So instead of shared flow, it's state flow, which means it only maintains the latest element that was sent to that flow or was published on the flow. So basically, what you can use it for is for UI state. So if you have multiple parts of your application, maybe an Android application that needs some state information, some data, and they want to read it from a single place that for which you're sure that that's the latest value, you can use mutable state flow. And whenever the state updates, you send it to that flow, and it will maintain the last state automatically in a nice suspending way. So how am I using them? Well, you can imagine that on the server, when a producer is producing messages, there might be multiple consumers listening to that topic, and all the consumers want all the messages. So you cannot use a simple channel because then you get like round robin basically, but you want all the consumers to receive all the messages. So what I do is I create per topic a mutable shared flow of, in this case, some data class called Kotka message, and I say also I want a replay size of 100, which means that whenever some consumer connects to that flow or starts collecting from the flow, you get the last 100 items if there are 100 or more. And so it remembers the last 100 and then it continues with whatever message is sent to that flow later. And well, to produce something on that flow, you call the emit function, and you can pass whatever payload you want. And for each consumer, you just launch a coroutine that says, well, I want to collect from that topic, and I want to send it to the specific connection that's for that client. And that can happen multiple times, of course. So, of course, things can go wrong, and you want to handle that gracefully. So let's start with the example of why do we need supervision? Well, imagine this call tree. Basically, all the blocks are coroutines, which means coroutine A is creating coroutine B and C is also creating D and E. And somewhere in E, something goes wrong. So for those who've seen my previous talk or know enough about coroutines, know that this means that because we're using structured concurrency, this will make sure that if E fails, then C will get cancelled as well. And because C is cancelled, D and A are also cancelled, and B is also cancelled. So you get a nice cleanup mechanism, which is nice when it's all related to each other and all connected. However, imagine we are sending or we are having multiple consumers, and each of these consumers has their own, context in which they do their thing, but you don't want, for example, if one consumer fails, that the other consumers are also cancelled. So in this case, you can use a thing called supervisor scope, which means that the parent coroutine, in this case S, is running in a supervisor scope. And whenever something goes wrong in one of the child coroutines, so in this case F, this means that C will still get cancelled. However, there's a protection which prevents S from being cancelled, which also prevents the other coroutine from being cancelled. So imagine we have two coroutines launched next to each other. The first one just prints a dot every second, very simple. And the second one waits for 3 seconds and then throws an error, saying, hey, something bad happened. In this case, by default, that means that, you get 3 dots and then the whole thing crashes because, everything gets cancelled. And you see the stack trace, which is convenient, but yeah, both of the coroutines are cancelled. So it's a very easy fix. You just wrap it in a supervisor scope, which means that the scope of the supervisor makes sure that every coroutine, every child coroutine that gets started from that scope cannot cancel the whole coroutine, so it cannot cancel the parent, so other coroutines can just continue. So in this case, that means that the printing of the dot just continues. After 3 seconds, you still see the stack trace. You still have to do your own error handling in case you need to act on that error, of course, and I'll leave that as an exercise to the viewers. But the rest just continues. So yeah, like I mentioned before, imagine you have multiple consumers reading multiple topics. In case one of the consumers fails, you still want the others to continue. And I just needed to wrap it in the supervisor scope and it worked. ThreadLocals. ThreadLocals? Yes, ThreadLocals. For the people doing enterprise Java or Kotlin development, they know that a lot of the frameworks use ThreadLocals to store some state during handling of a request coming from clients. So, for example, the current transaction, some information about security, something with distributed tracing, some logging context, etc. It uses ThreadLocals because basically every request is handled on its own thread. Well, in case of coroutines and in case of reactive programming, that doesn't really match because there you're not confined to a single thread. So if you're dealing with these kinds of libraries, then make sure to either see if you can use the reactive variant, for example, Spring RDBC for reactive database. You have a reactive Spring Security, and of course, other frameworks all have their own reactive counterparts. But for logging context, I just wanted to experiment a bit on how to deal with ThreadLocal state, even though you're not running on single threads. So to visualize the issue, if you have a certain coroutine, when it starts on whatever thread is available. And when it suspends, it's possible that it can resume on another thread. And then later it can suspend again. And it can resume maybe on the same thread, but the point is you're not sure on which thread your function is going to resume. And you should not care, because that's the whole principle with coroutines. But if there's something trying to read something from a thread local, that can go wrong because, well, there's no local thread. It can be any thread. So to deal with that, you have the principle of a thing called thread context element, which basically links your coroutine context with a thread local value. And the way that works is whenever your coroutine is started, you sort of get like a hook into that process to say, okay, when it starts, I want to replace the thread local value that's currently there with my own value, and remember the value that was there if there was any. And then the moment you suspend, you can restore the previously replaced value with in the thread local that's there, so that the thread is basically clean again. And whenever you resume and suspend, you do the same thing. You replace, restore, replace, restore. So it looks like a lot of code, but it's not that bad. Basically, you define a class that extends from thread context element, and it's a generic superclass which says, well, in this case, I want an optional string. And optional because, well, it could be that there's no value in the thread local, so it can be empty. So that's fine in this case. And what I do is I pass, in this case, a client ID, and that's the blue text you saw in the logging saying, hey, this is a producer for this topic or a consumer for this topic. And I create this context whenever I start something in the coroutine scopes. So those of you who see my previous talk know that the coroutine context is basically one big map with keys and values. The value can be whatever, and the key is basically what you define here as a singleton instance of the coroutine context key for, well, this type of class. So you know that it's a singleton, so there can only be one per coroutine. The update thread context method function gets called whenever your coroutine is starting or resuming on a specific thread. And in this case, this function returns a nullable string, as you can see, which is the type that's defined in the header. And the return value of this function should be the previous value that was there, if there's any. So in this case, I read the MDC context, which is basically a key value pair of items which are related to logging. So it's a logging context thing, for those that don't know. And in this case, I get the item, the value for the key client ID, which can be null, because there might not be a current item. And I also put the client ID I defined in my constructor as the current value for this coroutine. Whenever the coroutine gets suspended, or whenever it's finished, the restore thread context is run. And and whenever that restore thread context is called, you get the old state, which is the value you returned from the previous function. And you can restore that either in the logging context, or you can remove the item from the context in case the previous value was null. So you get a nice cleanup mechanism. And whenever you start the coroutine context for a specific client, in this case, which can be like a specific producer for a specific topic or specific consumer, you pass this MDC context element as an argument to the launch or to the with context function, whatever, and it gets added to the context and also to all the child coroutines that are present in that, well, that are started from that coroutine. So you don't have to do it every time you launch something, but only at the top, basically, because of the hierarchy way of working. Well, this might look like a bit of, a lot of code for just one logging context element. So don't worry, there's a library for this. It's called Kotlin Coroutines SLF4J, which integrates already with logging frameworks in Java. And they have a ready-made MDC context, which basically does the thing I just showed you, but then for everything on the logging context. And it works out of the box. But I just wanted to see how it works, so I made my own. But of course, if you're having the same issue, just use this one, and it works better. Well, you can imagine that during the development of the demo, sometimes things did not exactly work as planned, and I needed to debug a little bit. Well, luckily, there's also good support for that. So there's a Kotlin Coroutines debug library, which can be used in unit tests, or it can also be attached as a JVM agent to your production application. There's also a Kotlin Coroutines test library, which is also very convenient. I'm not showing this in the presentation, but I do have an example in the code, which is very nice because you can test your coroutines, but in a quick way. So even if you have delays of multiple seconds or minutes, it can run instantly because it uses sort of like a virtual time. So you can fast forward your coroutines, so they don't have to run fully, like use the full delay. But in case you're debugging a running application, you just want to see how things work, you can use this library. And it has a thing called debug probes, which basically work like thread dumps. So you can, at any moment in time, decide, okay, I want to see which coroutines are running at the moment, which are created, in which state are they, and it's very, very convenient. And they have a thing called blockhound, which detects if you're making blocking calls inside the coroutine context that should not be blocking. So how do we use the debug probes? Well, very easily. You call the debug probes.install somewhere in your Bootstrap code. And whenever you want to see whatever coroutines are running, you can call either debug probes.dump coroutines, which will dump the stack trace to the command line. Or in case of JVM agent, you can send a signal to the process to run it and show the coroutine dump. So what does the dump look like? Well, it's a big dump. So in this case, I had a small application in which I was running I started two coroutines and then called the dump coroutines function. And what you can see here is that there's one coroutine that's currently in the running state. And you see in the middle, you see at which line of code it's actually in. So in this case, I had some app, and line 14 is in the coroutines, in the class where it was currently executing. And you can also see where it was created, which is also nice, so extra information. So in this case, you see it was created at line 8, and it's currently running at line 14. And there's another coroutine which is in the created state, which means, well, it got created but didn't start running yet, and you can only see where it got created. So very, very nice way to see, like, hey, my application is hanging at some point. I did not expect that. Well, I can debug the coroutines and see, oh yeah, I forgot to close this one, or very, very convenient. So when did I use it in Kotka? Well, whenever it didn't work as expected, which, well, happened a few times. So. To summarize, channels, they can be used to connect senders and receivers to each other. Flows can be used to generate an asynchronous stream of data. Supervision is very nice if you want more fine-grained control on coroutine termination. Well, if you have to deal with ThreadLocals, luckily there's a way to do that, but try to prevent that and just go for reactive variants if possible. And debugging is very convenient at times, especially when you're in a time constraint, trying to get your demo up and running for a presentation. So some lessons learned. Despite the whole structured concurrency thing, which makes asynchronous code easier to read and to write, it's still sometimes hard to debug. It's still asynchronous code, so still things are happening in the way you might not expect them to. They're still more difficult than single-threaded synchronous code. So be aware that even though I'm saying things, hey, this is very nice and works very fine, you still might just be crazy trying to figure out why things are not working the way you're expecting them to work. For my demo, I sometimes used coroutines in certain scenarios where I was like, well, this can also just be a simple method call, but so not everything needs to be a coroutine. Sometimes being synchronous is just fine in specific use cases. Well, the Spring Webflux support for WebSockets in combination with coroutines was not out of the box supported, so it took a bit more time than anticipated. And the new feature of Kotlin, the context receivers, they work very nicely with the coroutine scope, because if you're writing coroutine scoped code, you often need some sort of scope to pass on to your functions, and context receivers work nicely to prevent you from having to give it as an argument to each function, or define it as an extension function on a coroutine scope. If you're interested in context receivers, there's a talk after this one which goes into the details for that one. Thank you. This was my presentation. I don't know if we have any time for questions.